What if everything we think we know about space is just the tip of the cosmic iceberg? Imagine gazing up at the night sky, feeling that familiar sense of awe, only to realize the universe might be far stranger, far more mysterious than we've ever dared to dream. From the moment humans first looked up, we've been captivated by the enigma of space, a vast expanse that seems to defy comprehension. Yet, despite centuries of study, the cosmos continues to surprise us, unraveling our assumptions and rewriting the rules right before our eyes. Today, we're diving deep into 30 mind-bending theories that shatter our understanding of reality itself. Ideas so extraordinary, they'll make you question the very fabric of existence. Think about the last time you heard a fact about space that left you speechless. Maybe it was the sheer scale of a black hole or the eerie silence between stars. Now picture this. What if space isn't empty at all, but humming with hidden dimensions, parallel universes, or even a cosmic hologram projecting our reality? These aren't just wild guesses, they're serious theories proposed by brilliant minds, each one a puzzle piece in the grand mystery of existence. Some suggest time might flow backward in distant galaxies, while others argue the universe could be a giant simulation coded by some unknown intelligence. And that's just the beginning. This journey isn't just about science, it's about the thrill of the unknown, the stories we tell to make sense of the infinite. Every theory we'll explore today is a doorway to wonder, a chance to step beyond the ordinary and glimpse the extraordinary. Whether you're a seasoned space enthusiast or just curious about the cosmos, these ideas will stretch your imagination to its limits. So buckle up, we're about to venture into the far reaches of possibility, where the rules of physics bend, reality twists, and the universe reveals its deepest, most astonishing secrets. Ready to have your mind blown? Let's begin. We've all heard the story. The universe began with a bang, an unimaginably hot and dense explosion that set everything into motion. But what if that wasn't the true beginning? What if the Big Bang was just a cosmic reset, a moment in an endless cycle of expansion and collapse? Some of the brightest minds in physics are challenging the idea of a singular starting point, proposing instead that our universe could be part of an eternal rhythm, like a breath in and out on a cosmic scale. Take the Big Bounce theory. It suggests that before the Big Bang, there was another universe that had already expanded, cooled, and eventually collapsed back in on itself. That collapse didn't lead to nothingness, but instead triggered the next explosion, birthing our own universe in an endless loop of death and rebirth. It's a mind-bending idea, but one supported by the mathematics of quantum physics, where even the most extreme conditions don't lead to true annihilation. Then there's Roger Penrose's controversial conformal cyclic cosmology, which argues that black holes might be seeds for new universes, carrying forward information from one cosmic era to the next in an infinite cycle. Even stranger, what if time didn't start with the Big Bang at all? Some models propose a pre-Big Bang phase, a mysterious epoch where the laws of physics as we know them didn't yet apply. Picture an unfathomable stretch of existence where space itself behaved differently, perhaps governed by forces we can't even detect anymore. It's like trying to imagine a world before light existed, utterly alien, yet somehow necessary for our reality to emerge. These aren't just wild philosophical musings, they're serious scientific attempts to answer one of the most profound questions we can ask. Did time and space truly have a starting point, or has the universe always found a way to renew itself? The more we learn, the clearer it becomes. Our cosmic origin story may be far stranger, far more ancient than we ever imagined. Now imagine this. What if our universe isn't alone, but just one page in an infinite cosmic library? The multiverse theory suggests exactly that, a reality where every possible version of existence plays out simultaneously, like endless variations of a story we'll never fully read. It's a concept that stretches the boundaries of imagination, yet it emerges from some of the most rigorous corners of physics. Start with bubble universes. Picture the cosmos as a vast ocean of space-time foam, where new universes constantly spring to life like bubbles in a boiling pot. Cosmic inflation, the rapid expansion thought to have shaped our early universe, could still be happening elsewhere, birthing countless other worlds with entirely different laws of physics. Some might have stronger gravity, others no light at all, each one a self-contained reality floating in a grander multiverse. And here's the kicker: if one of those bubbles collided with ours, it might have left scars in the cosmic microwave background, faint echoes we could one day detect. Then there's the many worlds interpretation of quantum mechanics, where every decision spawns a new universe. Did you choose coffee over tea this morning? In another reality, your alternate self did the opposite, and that split happens every instant at every quantum crossroads. It's not science fiction. It's a mathematical framework that avoids the paradoxes of traditional quantum theory by letting all possibilities play out somewhere. String theory takes it even further, proposing higher dimensions where universes hover like sheets of paper in a cosmic stack, each vibrating at unique frequencies. If true, gravity might leak between these membranes, explaining why it's so weak compared to other forces. Some versions even suggest entire universes could collide, triggering cataclysmic rebirths. The wildest part, these ideas aren't just philosophical musings, they're attempts to solve real mysteries, like why our universe's constants are perfectly tuned for life. If there are infinite universes, ours isn't special, it's just the lucky one where everything aligned. So next time you gaze at the stars, ask yourself, what breathtaking realities might exist just beyond the edge of our perception? What if everything we see, touch, and experience is nothing more than an illusion, a cosmic mirage projected from the edges of reality? The holographic principle turns our understanding of the universe inside out, suggesting that the three-dimensional world we inhabit might actually be encoded on a distant two-dimensional surface, like a movie playing on an invisible screen. This isn't just science fiction, it's a radical idea born from the study of black holes, where the laws of physics seem to twist into impossible knots. It all started with a paradox. When matter falls into a black hole, it vanishes from our universe, but according to quantum mechanics, information can never truly be destroyed. So where does it go? Physicists like Leonard Susskind and Gerard T. Hooft proposed a startling solution. The information isn't lost. Instead, it's somehow preserved on the black hole's event horizon, the point of no return, etched onto its surface like data on a cosmic hard drive. But here's where it gets wild. If that's true for black holes, could the same principle apply to the entire universe? Imagine the cosmos as a hologram. The vivid, three-dimensional reality around you, the depth of a starry night, the solidity of the ground beneath your feet might actually be a projection from a flat, two-dimensional boundary at the edge of everything. It's like those vintage holographic stickers that change when you tilt them, except on a scale so vast it redefines existence itself. The math even checks out. The equations describing events inside a volume of space can be perfectly mirrored by equations describing what happens on its surface. This theory flips our intuition upside down. Why would evolution give us senses tuned to a 3D world if it's all just a shadow play? Think of it like a video game. The graphics you see on screen, FEL, Chinese letter, but they're ultimately rendered from lines of code. Similarly, our brains might be decoding a lower dimensional reality into the rich tapestry of experience we know. Some researchers even speculate that this could explain why quantum particles behave so bizarrely. Their true source code might reside in that hidden 2D realm. The implications are staggering. If the holographic principle holds, it means space-time itself isn't fundamental, just an emergent property of deeper information processing. It challenges Einstein's view of a smooth, continuous universe, suggesting instead that reality might be pixelated at the tiniest scales, like a cosmic version of Minecraft. And if that's true, then free will, consciousness, even time could all be part of the projection, not fundamental truths, but features of the illusion. Yet for all its strangeness, this idea solves real puzzles. It bridges the gap between quantum mechanics and gravity, two frameworks that otherwise refuse to play nice. It offers a way to preserve information in the most extreme environments like black holes, and it hints that the universe might be far more interconnected than we ever realized, a single, seamless hologram where every part reflects the whole. So next time you look up at the stars, consider this. Their light, their vast distances, even your perception of them might all be part of an elaborate cosmic code written on the surface of reality itself. The universe could be whispering its secrets not in 3 dimensions but 2, a hidden language waiting to be deciphered. We think we know the universe, stars, galaxies, the vast emptiness between them. But here's the unsettling truth. Everything we can see, touch, or measure accounts for less than 5% of reality. The rest, an invisible, enigmatic force field known as dark matter and dark energy, pulling and pushing the cosmos in ways we barely understand. Picture an iceberg. The part above water is ordinary matter, the tiny fraction we recognize. Beneath the surface lies the real bulk of existence, dark and uncharted. Dark matter is the universe's hidden architect. We can't see it, can't touch it, yet its gravitational grip is unmistakable. Galaxies spin so fast they should tear themselves apart, but something unseen holds them together, an invisible scaffold weaving through space. Without it, the cosmos as we know it wouldn't exist. Think of it like wind. You don't see the air moving, but you feel its push. Watch trees bend under its force. Dark matter works the same way, its presence revealed only by how it tugs on stars, warps light, and sculpts the large-scale structure of the universe. Then there's dark energy, even more baffling. While dark matter pulls, dark energy pushes an anti-gravity force accelerating the expansion of the universe. Imagine blowing up a balloon with ink dots on its surface. As it inflates, the dots move apart. Now picture someone cranking the air pump faster and faster for no apparent reason. That's dark energy stretching spacetime itself, driving galaxies away from each other at increasing speeds. The terrifying implication: if this continues, distant galaxies will eventually vanish beyond an unreachable horizon, leaving future civilizations with a sky nearly empty of stars. Why can't we detect these colossal forces directly? Dark matter might be made of undiscovered particles that barely interact with light or matter ghosts slipping through our detectors. Some experiments hunt for faint flashes when these particles collide with atoms deep underground, but so far, silence. Dark energy is even trickier. It might be woven into the fabric of space itself, a property of the vacuum we don't yet comprehend. The irony is staggering. We've mapped the cosmic microwave background, landed probes on asteroids, photographed black holes. Yet 95% of reality remains a mystery. It's like spending your life studying shadows while the objects casting them stay just out of view. Some theories suggest extra dimensions or exotic quantum fields could explain these phenomena. Others wonder if we're missing something fundamental, a flaw in our understanding of gravity itself. What's clear is this: dark matter and dark energy aren't just footnotes in astrophysics. They're the dominant characters in the cosmic story, shaping everything from the birth of galaxies to the fate of the universe. And until we solve their riddles, we're like sailors navigating by starlight, unaware of the vast, unseen currents carrying us forward. What if your entire life, every memory, every sensation, even this very moment, was nothing more than lines of code running on some unfathomably advanced computer? The simulation hypothesis suggests exactly that. Reality as we know it might be an artificial construct, a meticulously crafted illusion indistinguishable from the real thing. It's an idea that's equal parts thrilling and terrifying, blurring the line between science fiction and serious scientific debate. Philosopher Nick Bostrom formalized this concept with his now famous trilemma. He argued that at least one of these statements must be true. Either nearly all civilizations go extinct before reaching technological maturity, or mature civilizations lose interest in creating simulated realities, or we're almost certainly living in a simulation right now. The logic is unsettlingly simple. If a civilization could one day run countless ancestor simulations, hyper-realistic recreations of their past, then the number of simulated minds would vastly outnumber biological ones. Statistically, the odds tilt heavily toward us being among the simulated, but this isn't just philosophy. Quantum mechanics adds eerie weight to the argument. Why does the microscopic world behave so strangely until observed? Some interpret the wave function collapse the moment particles, choose a state as evidence of computational optimization, like a video game only rendering details when a player looks at them. Even the speed of light might be a built-in processing limit, preventing the simulation from overloading. And then there's the pixelation of space-time itself. Just as a digital image breaks down into pixels when you zoom in, some theories suggest Planck length, the smallest possible unit of space, could be the universe's resolution limit. Of course, not everyone's convinced. Critics point out that simulating every particle in the universe would require unimaginable energy, perhaps more than the universe contains. But what if the simulation isn't rendering every detail? Think of how modern video games use procedural generation to create vast worlds without storing every tree or rock. Our universe might work similarly, with underlying algorithms filling in reality only as needed. The implications are dizzying. If we're in a simulation, do the simulated have rights? Could we ever hack the system? Some researchers have even proposed experiments to test the hypothesis, like hunting for glitches in physical constants or mathematical anomalies in quantum behavior. Yet, even if we found proof, would it change anything? Your joys, your struggles, your sense of wonder at the cosmos, they'd still feel real. And maybe that's the most mind-bending thought of all. Reality, simulated or not, is defined by our experience of it. Time might feel like an unstoppable river, carrying us from birth to death in a linear current, but what if that's all just a trick of perception? The block universe theory paints a radically different picture. Past, present, and future don't unfold in sequence but exist simultaneously, frozen in a vast four-dimensional tapestry. Picture a loaf of bread where each slice is a moment in time, already baked, already whole. Your childhood, this instant, even your final breath are all equally real, just occupying different coordinates in space-time. Einstein's relativity hinted at this when it showed time slowing down near black holes or speeding satellites. If time can stretch and warp, maybe it's not the rigid scaffold we imagine. Quantum mechanics adds another layer of weirdness. At the smallest scales, particles don't seem to care about chronological order. Experiments like the quantum delayed choice experiment suggest that present actions can retroactively influence past events, as if cause and effect are tangled in a knot. It's like dropping a pebble into a pond and watching the ripples move backward, a violation of common sense that makes perfect sense in the subatomic realm. Some physicists like Carlo Rovelli argue time might not even exist as a fundamental property. Instead, what we call time could be an emergent phenomenon, a byproduct of quantum interactions creating the illusion of change where there's only relation. Think of a movie reel. Each frame is static, but played in sequence, it creates motion. Our brains might be doing the same thing, stitching together discrete moments into a flowing narrative. Even memory reinforces the illusion. Recalling the past feels like accessing a distant file when, in the block universe, it's just another part of the eternal now. The implications are staggering. If time doesn't flow, free will becomes a puzzle. Are choices real or just predetermined threads in the cosmic fabric? Could future events already be influencing us like echoes rippling backward? Gravitational waves offer tantalizing clues. When black holes collide, they send ripples through space-time itself, distortions that treat time like just another dimension to bend. If time were truly fundamental, wouldn't it resist such manipulation? Yet here we are, measuring its elasticity with laser precision. Meanwhile, theories like loop quantum gravity propose that space-time is pixelated, with tiny atoms of reality flickering in and out of existence. In this view, time's smooth flow is a grand illusion, like watching a flipbook too fast to see the gaps between pages. So why does time feel so unshakably real? Evolution likely wired us to perceive it linearly, a survival tool for creatures navigating a world of cause and effect. But the universe operates on deeper rules, indifferent to our subjective experience. Whether time is emergent, illusory, or simply a dimension we're wired to misread, one thing's clear: the clock in your mind ticks to a rhythm that might not exist outside of it. The next time you glance at a clock, consider this: you're not just measuring moments, you're glimpsing a shadow of something far stranger. What if the vast distances between stars weren't an unbridgeable gulf, but a cosmic labyrinth filled with hidden shortcuts? Wormholes, those legendary tunnels through space-time, aren't just science fiction. They emerge straight from Einstein's equations, woven into the very fabric of general relativity as theoretical possibilities. Picture space as a sheet of paper folded so two distant points touch. A wormhole would be like poking a pencil through that fold, creating a bridge that bypasses the long journey across the surface. Einstein and physicist Nathan Rosen first explored this idea in 1935, dubbing them Einstein-Rosen bridges, mathematical solutions where space-time curves so drastically it stitches together distant regions like a celestial sewing project. But here's the catch: these cosmic tunnels are notoriously unstable. Imagine a soap bubble collapsing the moment you try to pass through it. Without some form of exotic matter, a substance with negative energy to prop open the throat of the wormhole, it would snap shut instantly, crushing anything daring enough to enter. Theoretically, this exotic matter could counteract gravity's inward pull, acting like cosmic scaffolding to keep the tunnel viable. The problem: we've never observed such matter in nature. Some quantum effects, like the Casimir force, hint at fleeting negative energy densities, but harnessing enough to stabilize a traversable wormhole remains firmly in the realm of speculation. Even if we solved that puzzle, navigation would be its own nightmare. Time dilation near a wormhole's mouth could mean emerging centuries after entering, or worse, arriving before you left, unleashing paradoxes that make time travel look tame. Then there's the issue of endpoints. A wormhole might connect not just two places, but two times or even two universes. Misjudge the exit, and you could find yourself stranded in an alien cosmos or a bygone era with no way back. Yet the allure persists. Wormholes offer a tantalizing solution to the Fermi Paradox. If advanced civilizations have mastered them, the silence of the cosmos might just mean everyone's traveling underground, bypassing the empty highways we're scanning. Recent research even suggests certain black holes might conceal wormholes at their cores, their immense gravity twisting space-time into a gateway rather than a dead end. So while we're centuries away from strolling through a stable wormhole, their theoretical existence reshapes how we think about connectivity in the universe. They remind us that space-time isn't just a stage, it's a dynamic, foldable fabric full of secrets waiting to be unraveled. The next time you gaze at the stars, remember, the shortest path to them might not be a straight line, but a twist in the very dimensions we call home. Black holes have long dominated our cosmic nightmares, regions of space where gravity wins so utterly, not even light escapes. But what if somewhere in the universe their exact opposites exist, not swallowing matter but violently expelling it? Meet white holes, one of the most tantalizing might-bess in theoretical physics. Imagine a black hole running in reverse instead of an inescapable pit, a cosmic geyser blasting out energy and particles at unimaginable speeds. The equations of general relativity allow for such objects, mathematically pristine yet never observed. They emerge as potential solutions when scientists trace black hole physics backward through time, like rewinding a film to see what came before the collapse. White holes aren't just mathematical curiosities, they could solve real cosmic puzzles. Take gamma-ray bursts, the most energetic explosions in the universe, capable of outshining entire galaxies for fleeting moments. These bursts release more energy in seconds than our sun will emit in its entire lifetime. Traditional explanations point to colliding neutron stars or supermassive black holes gobbling matter, but some theorists wonder if white holes could be the culprits. Picture a white hole's violent birth, a singularity erupting outward, ejecting all the material a black hole ever consumed in a cataclysmic fireball. The timing fits. White holes would be ephemeral, vanishing almost as quickly as they appear, much like the transient flashes of gamma-ray bursts, yet the challenges are glaring. White holes defy the second law of thermodynamics, which dictates that entropy, a measure of disorder, always increases. A white hole's sudden expulsion of ordered matter seems to reverse this flow, like unmixing cream from coffee. Some physicists argue quantum effects might permit such violations on microscopic scales, but scaling up to cosmic proportions remains contentious. Others propose white holes could be the other end of black holes in a hypothetical Einstein-Rosen bridge, with matter falling into a black hole here only to erupt from a white hole elsewhere. It's a poetic idea, cosmic recycling on an unimaginable scale, but without evidence, it lingers in the realm of speculation. Then there's the ultimate question: if white holes exist, where are they? The universe is old enough that any primordial white holes should have long since exhausted their energy, fading into obscurity, unless, of course, they're still forming. Some models suggest quantum fluctuations in spacetime itself could spontaneously birth white holes, though the conditions required border on the fantastical. Alternatively, what we perceive as the Big Bang itself might have been the ultimate white hole event, a singularity bursting forth to create our universe. It's a dizzying thought that our entire cosmic history could be the aftermath of something erupting rather than collapsing. Whether white holes are real or just elegant math, they push us to rethink the boundaries of physics. They remind us that the universe's playbook might include chapters we haven't yet imagined, where the rules reverse and creation springs from destruction. Until we detect one, they remain cosmic phantoms, teasing us with the possibility that somewhere, somehow, the universe is exhaling what black holes have inhaled. What if consciousness isn't something the universe produces like trees producing fruit, but something the universe fundamentally is? This is the radical proposition of panpsychism, a theory that suggests awareness isn't confined to brains but woven into the fabric of reality itself. Imagine every particle, every star, every ripple in spacetime humming with a faint hum of subjective experience. It sounds like mysticism, but some of the brightest minds in physics and philosophy argue it might be the missing link in our understanding of existence. At its core, panpsychism flips the traditional view of consciousness on its head. Instead of treating it as an emergent property of complex systems like brains, it posits that even the simplest forms of matter possess some rudimentary form of experience. Not human-like thought, of course, but a primal, microscopic version of feeling. Think of it like this: an electron might not ponder philosophy, but it could have a whisper of interiority, a bare sliver of being. This isn't about assigning emotions to rocks. It's about recognizing that the boundary between mind and matter might be far blurrier than we've assumed. Why would anyone take this idea seriously? Start with the hard problem of consciousness, coined by philosopher David Chalmers. Science excels at explaining how brains process stimuli, how light becomes vision, sound becomes hearing, but it's utterly silent on why these processes should feel like anything at all. Why isn't the universe just a vast, unfeeling machine? Panpsychism offers an elegant, if provocative, solution because feeling is baked into the machine's gears from the start. Quantum mechanics adds another layer of intrigue. Particles at the subatomic level behave differently when observed, as if aware of being watched. While most physicists dismiss this as metaphor, panpsychists wonder, what if the metaphor points to something deeper? Could the collapse of the wave function the moment a particle chooses its state be a primitive form of decision-making, a flicker of proto-consciousness? Even integrated information theory, a leading neuroscientific model, suggests consciousness arises from the way systems organize and share data, a property that, in theory, needn't be exclusive to brains. Critics, of course, aren't convinced. They argue panpsychism trades one mystery for another, replacing the puzzle of emergent consciousness with an equally baffling claim about atoms having inner lives. Others worry it's unfalsifiable. How would you test whether a quark has subjective experience? But proponents counter that all theories of consciousness face gaps, and at least panpsychism avoids the paradox of something as vivid as experience springing from entirely insentient parts. The implications are staggering. If consciousness is universal, then the cosmos isn't just a cold, indifferent void. It's a vast network of experience, from the dull hum of dust to the symphony of a thinking brain. It might even reshape how we approach artificial intelligence. Could a sufficiently complex computer truly feel, or would it just simulate feeling? And what does it mean for our place in the universe if awareness isn't a fluke, but a fundamental thread in the cosmic tapestry? Whether panpsychism holds up or not, it forces us to confront the deepest question of all. What is reality, if not something that's observed, felt, and lived? The answer might not lie in the stars, but in the very nature of existence itself, a universe not just full of mysteries, but alive with them. The universe is unimaginably vast, with trillions of galaxies, each containing billions of stars. So where is everybody? This is the haunting core of the Fermi Paradox, the glaring contradiction between the high probability of alien civilizations and our complete lack of evidence for them. Named after physicist Enrico Fermi, who famously posed the question during a casual lunch discussion in 1950, this paradox has spawned some of the most unsettling and fascinating theories in science. First, consider the Great Filter. This chilling idea suggests that somewhere between the emergence of life and the development of galaxy-spanning civilizations, there's a nearly insurmountable barrier that wipes out intelligent species before they can make contact. It could lurk in our past. Maybe complex life is astronomically rare and Earth got impossibly lucky. Or worse, it might await us in the future. Climate collapse, nuclear war, rogue AI, any could be the universal traps that snuff out civilizations just as they reach technological maturity. The eerie silence of the cosmos might be a graveyard's quiet, filled with species that flamed out before they could leave their mark. Then there's the zoo hypothesis, a concept as intriguing as it is humbling. What if advanced civilizations know we're here but deliberately avoid contact, treating Earth like a nature preserve? Imagine ants in a rainforest, unaware of the scientists observing them from a distance. This isn't just speculation. It aligns with the prime directive from Star Trek, but with a darker twist. Maybe they're not benevolent observers but indifferent ones, or worse, we're intentionally isolated for reasons we can't comprehend. Alternatively, think about the limitations of our own perception. Human technology has only been capable of scanning for extraterrestrial signals for a blink of cosmic time. Advanced civilizations might communicate in ways we don't yet recognize, using neutrino beams, quantum entanglement, or something entirely beyond our physics. It's like searching for radio signals in the Middle Ages. You wouldn't find any, not because they didn't exist, but because your tools were centuries away from inventing them. Some theories go even further. perhaps intelligent life inevitably turns inward, creating virtual realities so compelling they lose interest in exploring the physical universe. Or maybe civilizations self-destruct once they harness certain technologies, like nanotechnology or artificial superintelligence. There's even the dark forest hypothesis, which paints the cosmos as a lethal game of hide and seek, where any civilization that reveals itself is quickly eliminated by others fearing competition. The most haunting possibility: we might be alone. Earth could be a fluke, a 1 in a trillion accident in a universe otherwise void of conscious observers. But whether the answer is grim or hopeful, the Fermi Paradox forces us to confront our place in the cosmos like nothing else. It's not just a question about aliens, it's a mirror reflecting our future, our fragility, and the profound responsibility that comes with being the only thinking matter we know. Suppose you're in a life-threatening situation, a car crash, a fall from a great height, and in that split second, death seems inevitable. But miraculously you survive. Coincidence, luck, or something far stranger, quantum immortality is the spine-chilling theory that you can't die, at least not from your own perspective. It's not about defying physics, but about how consciousness might navigate the infinite branches of the multiverse, always landing in a timeline where you persist. This idea springs from the many worlds interpretation of quantum mechanics, where every possible outcome of an event spawns a new universe. Normally, we think of these branches as parallel realities where every choice plays out, some where you took that job overseas, others where you never existed. But quantum immortality takes it further. At the moment of death, your consciousness shifts to a version of reality where you survive. From your viewpoint, you'd never experience death, only a string of improbable survivals, like a cosmic game of chance where you always draw the winning card. Think of Schrödinger's famous cat, both alive and dead in its box until observed. In the many worlds view, there's no single outcome, just two separate universes, one with a living cat, one with a corpse. Now replace the cat with you. Quantum immortality suggests your consciousness is tethered to the versions of reality where you're still breathing. Even if the odds of survival are 1 in a billion, there's always a timeline where you make it, and that's the one you'll experience. The implications are dizzying. Would aging work the same way? Could you find yourself in a future where medical technology keeps you alive far beyond natural limits? Some thought experiments take this further. Picture a suicidal gambler playing Russian roulette with a million-chambered gun. Statistically, they should die, but from their perspective, the gun keeps miraculously clicking on empty chambers. To outside observers, they'd see deaths in most timelines, but the gambler's consciousness would only inhabit the one where they inexplicably survive. But here's the philosophical gut punch. If this is true, how would you ever know? Death becomes something that happens to other versions of you, while your experience rolls forward indefinitely. It's a solipsistic nightmare where you're the center of a reality that continually reshapes itself to keep you in the game. Critics argue this is unfalsifiable after all. Dead people can't report their experiences, but proponents counter that it's a logical extension of many worlds, forcing us to grapple with what consciousness really is. Is it comforting or terrifying? That depends on your perspective. On one hand, it hints at a form of immortality woven into the fabric of reality. On the other, it suggests an eternity where you're always the last one standing, watching countless versions of yourself vanish into the cosmic static. Either way, quantum immortality blurs the line between science and metaphysics, leaving us with an unnerving question. What does it mean to be alive if death is just a doorway your consciousness never walks through? Consider the most unsettling thought experiment of all. What if you're not a person with a lifetime of memories, but a fleeting hallucination, a self-aware illusion that blinked into existence mere moments ago? This is the essence of the Boltzmann brain paradox, a cosmic riddle so bizarre it threatens to unravel our entire understanding of reality. Named after physicist Ludwig Boltzmann, who pioneered statistical mechanics, the paradox emerges from a simple but terrifying calculation. In an infinite universe governed by entropy, the tendency toward disorder, random fluctuations can occasionally create order from chaos. Given enough time, even the most improbable events become inevitable. And here's the kicker: statistically, it's far more likely for a single, fully formed brain to spontaneously assemble from the void, complete with false memories of a past, than for an entire, ordered universe like ours to exist. Picture a vast, empty cosmos simmering with quantum foam. Over trillions of years, particles randomly collide, and by sheer chance, they might briefly arrange themselves into a functioning human brain. Not attached to a body, not born from evolution, but a lone, self-aware entity floating in darkness, convinced it's lived a full life. This Boltzmann brain would have no way to tell it isn't real. Its memories of childhood, relationships, even watching this video, all would be fabricated, written into its structure by the accident of its creation. The truly unsettling part: if the universe lasts forever, Boltzmann brains should vastly outnumber real, biologically evolved minds like ours. So why does reality feel so stable and coherent? The paradox forces cosmologists to confront deep flaws in our understanding of time and existence. If Boltzmann brains are more probable than ordinary observers, why aren't we one of them? Some theories suggest our universe's low entropy beginnings, the Big Bang's inexplicable order, might be evidence of something even stranger at work. Perhaps the laws of physics we know are just local bylaws in a grander multiverse, or maybe there's an undiscovered principle preventing Boltzmann brains from forming. Others argue consciousness itself might be immune to such random fluctuations, anchored to genuine causal histories in ways we don't yet grasp. Then there's the nightmare scenario. What if we are Boltzmann brains, destined to dissolve back into chaos the moment this thought completes? The only solace is that if that were true, you'd never know. Like a dreamer waking to erase the dream, the universe would forget you as quickly as it conjured you. This isn't just philosophical navel-gazing, it's a serious challenge to cosmological models. If a theory predicts Boltzmann brains should dominate reality, yet we find ourselves in a structured universe, that theory might be fatally flawed. Yet for all its existential dread, the Boltzmann brain paradox highlights something profound: the fragility of existence. It reminds us that reality, as we experience it, rests on a knife's edge between order and chaos. And that maybe, just maybe, the very fact we're here questioning it is the best evidence we're not illusions after all. The next time you recall a cherished memory, ask yourself, how do you know it's real? The answer might hinge on the deepest mysteries of the cosmos. What if the Big Bang wasn't a fiery beginning, but the echo of a cosmic collision, a shiver rippling through higher dimensions we can't even see? This is the wild promise of the ekpyrotic universe model, a theory that rewrites our origin story not with a bang but with a crash. Imagine two vast parallel sheets of reality, membranes, or brains for short, floating in a higher dimensional space. These aren't just abstract concepts, they're central to string theory, which suggests particles are tiny vibrating strings and the universe might have up to 11 dimensions. Now picture those colossal brains drifting, drawn together by gravity across dimensions we can't perceive, until smash, they collide. The energy of that impact could have ignited everything: the heat, the light, the sudden expansion we call the Big Bang. The ekpyrotic model turns traditional cosmology on its head. Instead of a singularity exploding from nothing, our universe emerges from something tangible, an event with a before and after. Think of it like clapping your hands. The sound isn't born from nothingness, but from the force of two surfaces meeting. Here, the brains are those hands, and the Big Bang is the thunderclap. This idea solves one of the biggest puzzles of the standard Big Bang theory. Why was the early universe so unfathomably smooth? Observations show matter distributed with near-perfect uniformity. something the classic model struggles to explain without invoking an ad hoc inflation period. But if the universe began with a collision, the brain's flat, uniform surfaces would naturally imprint that order onto our cosmos, no inflation required. String theory breathes life into this scenario. In this framework, brains aren't just mathematical quirks, they're dynamic objects where open strings can anchor, effectively trapping particles and forces onto the brain. That's why we perceive only 3 spatial dimensions. Everything we know might be stuck like bugs on a windshield, oblivious to the wider dimensional highway beyond. When brains collide, the energy could excite those trapped strings, flooding our newborn universe with particles and radiation. Even dark matter might find an explanation here. Some particles could be remnants of the collision, lurking in hidden folds of the brain. But the ekpyrotic model isn't without controversy. For one, it requires extra dimensions, something we've never observed. And while it elegantly explains uniformity, it struggles with other cosmic quirks, like the slight temperature variations in the cosmic microwave background. Some critics argue it's just replacing one mystery, the Big Bang's origin, with another, the brain's existence. Yet proponents counter that the model offers testable predictions, like specific gravitational wave patterns that future observatories might detect. The most tantalizing implication, cyclic rebirth. If brains collide once, they could collide again. An endless cycle of universes being born, expanding, cooling, and eventually drawn back together for another cosmic reset. No singular beginning, no heat-death finale, just an eternal dance of creation and destruction. It's a vision far grander than the Big Bang's one and done narrative, painting time itself as something boundless. So next time you hear about the Big Bang, remember, it might not have been the start of everything, just the latest chapter in a saga written across dimensions beyond our sight. What if the entire universe, every galaxy, every star, even the space between them is nestled inside a black hole? This mind-bending theory suggests our cosmos might not be the top-level reality, but instead a hidden realm within the crushing depths of a singularity belonging to a far grander universe. It sounds like science fiction, but the math actually checks out. When you examine the equations describing black holes and the birth of our universe, eerie parallels emerge, hinting at a connection deeper than we ever imagined. Start with the birth of the cosmos. The Big Bang describes a moment of infinite density, a singularity just like the heart of a black hole. But what if that wasn't the beginning of everything, just the moment our pocket of reality formed? Imagine a supermassive black hole in some higher dimensional parent universe, its gravity so intense that space-time collapses inward. At the moment of singularity, instead of destroying everything, that collapse could have rebounded, birthing an entirely new space-time continuum, our universe. In this scenario, the Big Bang isn't a one-time event, it's the natural outcome of a black hole's formation elsewhere. This idea gains traction when you compare the behavior of black holes to cosmic expansion. A black hole's event horizon, the point of no return, acts like a one-way membrane. Nothing inside can escape, but from the perspective of someone inside, that horizon isn't a wall, it's an infinite boundary expanding faster than light can traverse it. Sound familiar? It's uncannily similar to how we describe the observable universe's edge, where distant galaxies recede faster than light due to cosmic expansion. Could the universe's horizon be a black hole's event horizon, just viewed from the other side? Even more striking is how black holes preserve information. Quantum mechanics insists information can't be destroyed, yet black holes seem to erase it when matter crosses the singularity. Some physicists propose the information isn't lost, it's encoded on the event horizon's surface like a hologram. Now apply that to our universe. If we're inside a black hole, the cosmic microwave background, the afterglow of the Big Bang, might not just be random noise. It could be a scrambled imprint of the parent universe's information, projected onto our event horizon at the beginning of time. The implications spiral outward. If our universe is a black hole, there could be countless others, each with their own physics, nested like cosmic matryoshka dolls. Some might have stronger gravity, others extra dimensions, each one a unique experiment in reality. It even offers a fresh take on dark energy. The outward pressure we perceive as accelerating expansion could be the residual push from that primordial collapse, like a spring still rebounding from its compression. Critics argue this theory has gaps, like explaining how a black hole's interior could sustain complexity long enough to form galaxies, rather than collapsing into chaos. But proponents counter that the extreme conditions near a singularity might spawn entirely new physical laws, ones where matter organizes rather than disintegrates. Either way, the idea forces us to rethink not just our origins, but the very nature of existence. Are we the main event, or just a shadow cast by something vaster? The next time you look up at the night sky, consider this. You might not be gazing out into the cosmos, but staring at the walls of a prison you can never see beyond. We've all heard the universe will end in fire or ice, either collapsing back into a singularity or fading into eternal darkness. But what if the true end isn't heat death or a big crunch, but something far more violent? Enter phantom energy, a hypothetical form of dark energy so destructive, it wouldn't just accelerate the universe's expansion, it would shred space-time itself in a catastrophic event cosmologists call the Big Rip. Picture this: dark energy isn't just pushing galaxies apart, it's growing stronger over time, its repulsive force escalating until not even atoms can hold themselves together. First, galaxies would be torn from each other, then stars ripped from their orbits, planets pulled apart molecule by molecule, until finally, space-time itself fractures at the seams. Phantom energy's power comes from its equation of state, a measure of how its pressure relates to its energy density. Ordinary dark energy has a value just below -1, but phantom energy pushes past that threshold, making its gravitational push intensify as the universe expands. It's like a car whose accelerator gets stickier the faster you go, until eventually you're hurtling toward a wall with no way to brake, the scariest part. If this theory holds, the countdown isn't measured in billions of years. Some models suggest the Big Rip could happen in as little as 22 billion years from now, cosmically speaking, the blink of an eye. But how would it unfold? Stage 1, galaxy clusters already drifting apart lose their gravitational bonds entirely, vanishing over each other's horizons like ships in a fog. Next, individual galaxies unravel, stars scattering into the void. Then, as phantom energy's grip tightens, planetary systems are dismantled, gas giants like Jupiter ripped from their suns, Earth flung into the abyss. In the final moments, gravity and nuclear forces lose their grip. Stars explode as their own gravity can no longer counteract the phantom tide. Planets crumble into dust. Then, atoms themselves disintegrate, protons and neutrons torn apart. Finally, space-time, the very fabric of reality, snaps like an overstretched rubber band. Is this inevitable? Not necessarily. Phantom energy remains hypothetical, and many physicists argue the equation of state could never cross that critical threshold. Yet the mere possibility forces us to confront a haunting truth. The universe's fate might not be a slow fade, but a violent crescendo. Whether it's 22 billion years away or never happens at all, the Big Rip reminds us that the cosmos runs on forces beyond our control, and even the fabric of reality isn't guaranteed to last forever. Ever had that eerie feeling where you swear something happened a certain way only to discover reality disagrees? You're not alone. The Mandela effect describes those bizarre moments when large groups of people share identical false memories, often about pop culture or historical events. The name comes from one infamous example. Countless people vividly remember Nelson Mandela dying in prison during the 1980s, complete with news coverage and public mourning, except he didn't. He was released, became South Africa's president, and passed away in 2013. So why do so many recall an event that never occurred? Some chalk it up to faulty memory, but others wonder, could these glitches hint at something far stranger, like parallel realities brushing against our own? Think of reality as a vast cosmic tapestry woven from countless threads representing every possible outcome. In a multiverse, every decision splits the timeline somewhere. Mandela did die in prison, and somewhere else, you took that job overseas instead of staying home. Normally, these universes stay separate, but what if they occasionally leak? Quantum mechanics allows for superposition particles existing in multiple states until observed. Some theorists suggest consciousness itself might act as an observer, collapsing possibilities into a single timeline. But if observation locks in reality, could brief moments of quantum uncertainty let fragments of other timelines bleed through? Those shared false memories might be echoes of events that did happen, just not here. Then there's simulation theory. If we're living in an advanced virtual world, the Mandela effect could be glitches in the code, like a video game accidentally loading assets from a deleted save file. Ever noticed how many examples revolve of pop culture? The Berenstain Bears misremembered as Berenstein, Darth Vader's "Luke, I am your father" line he actually says, "No, I am your father," or the Monopoly Man's non-existent monocle. These aren't obscure trivia, they're cultural touchstones repeated millions of times. In a simulation, frequently accessed data might corrupt more easily, like a scratched DVD skipping in the same spot for everyone. But here's where it gets truly unsettling. Some false memories have eerie consistency. People who recall Mandela's death in prison describe the same funeral speeches, the same news anchors reporting it details too specific for coincidence. Similarly, many swear they saw a Sinbad genie movie called Shazam in the 90s, even sketching identical cover art. No such film exists, yet the shared details are uncanny. Could these be residual memories from timelines where those events were real? Or perhaps moments when the simulation briefly flickered, overlaying alternate versions of reality? Skeptics argue these are just quirks of how human memory works, our brains filling gaps with plausible details influenced by suggestion. After all, memory isn't a recording, it's a reconstruction easily warped by time and social reinforcement. But that doesn't explain why these false memories cluster around specific, often trivial details while leaving surrounding context intact. Why misremember a single line in Star Wars but recall the rest of the scene perfectly? Whether the cause is quantum overlap, simulation glitches, or simply the fallibility of our minds, the Mandela effect forces us to confront a humbling question: how much can we trust our own recollections? If reality is more fluid than we thought, if the past can shift beneath our feet, then what does that mean for truth itself? Next time you're certain something happened a certain way, pause and wonder, is this your memory, or did you borrow it from another version of you in a universe just out of reach? At the smallest scales imaginable, far smaller than atoms, even tinier than the particles within them, space-time itself might not be the smooth, unbroken fabric we assume. Instead, picture a seething, frothy chaos, a turbulent ocean of fluctuations where space and time churn unpredictably. This is the bizarre realm of quantum foam, a concept born from the collision between two titans of physics, quantum mechanics and general relativity. While Einstein's theory paints gravity as the curvature of a serene spacetime landscape, quantum mechanics insists that the subatomic world is a storm of uncertainty, where particles flicker in and out of existence. Quantum foam is where these two worlds meet, or more accurately, where they violently disagree. The idea traces back to physicist John Wheeler in the 1950s. He proposed that at scales around the Planck length, a distance so small it's a trillion times tinier than an atom, spacetime loses all semblance of order. Instead of a continuous fabric, it becomes a turbulent froth, bubbling with temporary wormholes, microscopic black holes, and distortions that appear and vanish in fractions of a second. These fluctuations aren't just empty theorizing, they're a direct consequence of Heisenberg's uncertainty principle, which states that at quantum scales, energy can't be pinned down to a single value. This means empty space is never truly empty. It's a boiling soup of virtual particles and fleeting spacetime distortions, constantly borrowing energy from the universe to exist for the briefest moments before vanishing back into the void. Imagine looking at a calm pond with the naked eye. It seems perfectly still, but zoom in with a microscope and you'll see molecules jostling chaotically. Quantum foam takes this to the extreme. The very ground beneath the particles we know might be a maelstrom of microscopic black holes tunneling in and out of existence, or even fleeting bridges to other regions of spacetime. Some theories suggest these bubbles of foam could occasionally merge or swell, creating detectable ripples in spacetime itself, gravitational waves from the quantum underworld. Yet for all its theoretical elegance, quantum foam presents a massive challenge. It implies that at the tiniest scales, spacetime isn't just bumpy, it's undefined, like a movie reel with missing frames. This wreaks havoc on our attempts to unify physics. General relativity relies on smooth spacetime, while quantum foam suggests that smoothness is an illusion, emerging only when we zoom out. It's like trying to build a castle on quicksand. Our foundational theories might be standing on ground that doesn't truly exist. Could we ever observe this foam? Direct detection is nearly impossible. The scales involved are so minute. Even our most advanced particle colliders can't probe them, but some scientists propose indirect methods. If spacetime is frothy, light traveling vast cosmic distances might scatter off these fluctuations like a shimmering mirage in the desert. Gamma-ray bursts, the most energetic explosions in the universe, could hold clues. Their photons traverse billions of light years, and if quantum foam exists, high-energy photons should arrive slightly later than lower-energy ones, a delay caused by bouncing through the foam's texture. So far, results are inconclusive, but the hunt continues. Quantum foam isn't just a curiosity, it's a battleground for the future of physics. If confirmed, it could revolutionize our understanding of reality's building blocks, showing that even the stage of the universe is built from something far stranger than we dreamed. Until then, it remains one of the most tantalizing and frustrating hints that the cosmos is wilder, messier, and more enigmatic than our theories can yet capture. What if you could hold a structure in your hand that moves without ever stopping, not because it's alive or powered, but because it exists in a perpetual dance with time itself? This isn't science fiction, it's the mind-bending reality of time crystals, a bizarre phase of matter that defies everything we thought we knew about physics. Unlike ordinary crystals, which repeat their atomic patterns in space, think of the symmetrical lattices of diamonds or snowflakes. Time crystals repeat in time. They oscillate, flip, or cycle through states with clockwork regularity, not because energy is being pumped into them, but because it's baked into their very existence. It's like finding a pendulum that swings forever without friction or a clock that ticks endlessly without winding. The discovery of time crystals sent shockwaves through the scientific community. For decades, physicists assumed such structures were impossible, violating the sacred laws of thermodynamics. Energy can't be created from nothing, and systems tend toward disorder. So how could something exhibit perpetual motion without an external push? The breakthrough came in 2012 when Nobel laureate Frank Wilczek theorized that under certain quantum conditions, a system could settle into a stable, repeating pattern without violating energy conservation. The key: time symmetry breaking. Just as a spatial crystal breaks the symmetry of empty space by repeating a structure, a time crystal breaks the symmetry of time by repeating a motion. A decade later, experiments with ion chains and diamond impurities proved him right. creating the first lab-grown time crystals that pulsed like tiny cosmic metronomes. So how does it work? Imagine a ring of atoms, each with a quantum property called spin, like a tiny compass needle pointing up or down. In a normal magnet, these spins align to form a static pattern. But in a time crystal, they refuse to settle. Even in their lowest energy state, the spins flip back and forth in a never-ending cycle, locked in a rhythm dictated not by external forces but by the intrinsic rules of quantum mechanics. It's as if the atoms are trapped in an eternal game of musical chairs, forever switching seats without anyone calling the tune. The implications are staggering. Time crystals could revolutionize quantum computing, where maintaining stable, coherent states is the holy grail. Traditional qubits' quantum bits are fragile, easily disrupted by tiny disturbances. But a time crystal's inherent rhythm might shield quantum information, acting as a built-in error corrector. Picture a quantum hard drive that doesn't just store data, but actively protects it by cycling through states, like a vault that rearranges its locks faster than any thief can pick them. Some researchers even speculate these structures could hint at new physics beyond the standard model, perhaps unlocking secrets about time's arrow or the quantum nature of gravity. Here's the real kicker. Time crystals exist at the edge of equilibrium, in a twilight zone between order and chaos. They're not perpetual motion machines. They don't do work or generate energy, but they challenge our intuition about what's possible in a universe bound by entropy. Could they occur naturally in extreme environments like neutron stars or the aftermath of the Big Bang? Might time itself, on some fundamental level, have a crystalline structure we've yet to perceive? For now, these questions linger at the frontier of physics, but one thing's certain: time crystals have shattered the illusion that matter must be static or passive. They're proof that the universe still holds surprises, not just in the vastness of space, but in the silent, rhythmic ticking of the quantum realm. What if the universe isn't just governed by physics, but is running physics, like some cosmic supercomputer crunching the numbers of reality itself? This is the radical proposition of quantum computing pioneer Seth Lloyd, who suggests the cosmos might not merely obey the laws of quantum mechanics. It could be a quantum computer, processing the information of existence one calculation at a time. Forget silicon chips and circuit boards. The hardware here is space-time itself, and the software is everything from quarks to quasars. Let's break this down. In conventional computing, bits flip between zeros and ones to perform operations. Quantum computers use qubits, which can be 0, 1, or both simultaneously, a superposition that allows parallel processing on a mind-boggling scale. Now imagine the universe doing this naturally. Every particle interaction, electrons orbiting atoms, photons streaming from stars, could be a quantum computation, with particles acting like qubits and the fundamental forces as the operating system. Even the randomness of quantum events might not be chaos, but the universe choosing outcomes through a kind of cosmic processing. Lloyd's math reveals something astonishing: the universe's computational limits. Based on its age, about 13.8 billion years, and observable volume, he calculates it could have performed around 10 to the power of 120 operations since the Big Bang. That's not just a big number, it's a theoretical ceiling for how much calculating reality could have done to arrive at its current state. Every chemical reaction, every galaxy collision, even your thoughts right now, all could be steps in an unimaginably vast computation unfolding since the dawn of time. But here's where it gets wild. If the universe is computing itself, what's the program? Some suggest it's simulating its own laws: gravity, electromagnetism, like a self-referential loop where the rules create the system that enforces them. Others propose consciousness plays a role, with observation collapsing quantum possibilities into definite outcomes, not just at human scales but universally. Picture the double-slit experiment, where particles behave as waves until measured but scaled up. The universe might resolve reality only when observed by some larger process. Critics argue this is metaphysics dressed as physics, that calling the universe a computer is just a metaphor. After all, traditional computers are designed for specific tasks, while the cosmos shows no obvious programming goal. But proponents counter that evolution itself resembles an algorithm, iterating through possibilities until complexity emerges. Even entropy, the slow march toward disorder, mirrors computational heat dissipation. And if quantum fields encode information at the Planck scale, then every cubic centimeter of empty space could be humming with data storage beyond our comprehension. The implications ripple outward. If reality is computational, could we someday hack it, rewriting physics like editing code? Might black holes be cosmic garbage collectors, compressing information into singularities? And if the universe has finite processing power, does that mean it could one day run out of memory? These aren't just thought experiments, they're windows into a view of existence where math isn't just the language of physics, but its very substance. So next time you feel the sunlight on your skin, consider you might not just be standing in the universe, you could be part of its operating system. Imagine throwing your most precious book into a fire, watching the pages blacken and crumble into ash. Now picture this: every single word, every ink stroke is somehow preserved in the smoke rising from the flames. That's the essence of the black hole information paradox, a puzzle so profound it pits quantum mechanics against general relativity in a battle for the soul of physics. At its heart lies a simple question: when something falls into a black hole, is its information truly destroyed, or does the universe find a way to keep it hidden? For decades, physicists assumed the answer was grim. Black holes, after all, are cosmic one-way streets. Once matter crosses the event horizon, it's gone forever, crushed into the singularity where even the laws of physics break down. But quantum mechanics has a sacred rule: information can never be lost. Whether it's the spin of an electron or the DNA sequence of a long-extinct dinosaur, every detail of the universe's history must, in principle, be recoverable. So when Stephen Hawking showed in the 1970s that black holes slowly evaporate, emitting what we now call Hawking radiation, it created a crisis. If a black hole vanishes, taking its secrets with it, where does the information go? Hawking initially believed it was erased, a conclusion that would mean rewriting quantum theory itself. The holographic principle offered a way out. Inspired by black hole thermodynamics, physicists like Leonard Susskind and Gerard T. Hooft proposed that information isn't lost, it's encoded on the black hole's event horizon, the boundary where light can no longer escape. Picture a library where books aren't stored on shelves but printed on the walls. As matter falls in, its information gets smeared across this two-dimensional surface like ink on a page, preserved in the distortions of space-time itself. Hawking radiation, then, isn't random noise, it's a slow leak of that encoded data, a cosmic whisper revealing the black hole's hidden history. Recent breakthroughs have turned this theory into a battlefield. In 2016, Hawking himself, along with colleagues Malcolm Perry and Andrew Strominger, suggested that black holes might have soft hair, subtle, low-energy disturbances around the event horizon that could carry information. Think of it like static on an old TV, seemingly random, but actually packed with hidden signals. Meanwhile, quantum gravity researchers have turned to string theory and loop quantum gravity, searching for ways information might escape or be stored in the black hole's quantum structure. Some even propose that black holes don't evaporate entirely but leave behind microscopic remnants, information, dense fossils preserving every bit of what fell in. Yet mysteries linger. If information escapes via Hawking radiation, how does it stay intact after being scrambled by the violent forces near the singularity? Imagine trying to reconstruct a shredded document from the ashes of a bonfire, possible in theory, but devilishly complex in practice. And what happens to an astronaut falling into a black hole? From the outside, their information is painted on the horizon, but from their perspective, they plunge straight through. This firewall paradox suggests either our understanding of gravity is flawed or quantum mechanics needs a radical update. The stakes couldn't be higher. Solving this paradox could unlock the theory of everything, a framework uniting quantum mechanics and gravity. It might reveal whether reality is fundamentally digital, with space-time itself built from information bits, or if deeper layers of physics remain hidden. Already, labs are simulating black hole dynamics with quantum computers, while telescopes hunt for echoes of Hawking radiation in the cosmos. Every clue brings us closer to answering a question that cuts to the core of existence. In a universe governed by both chaos and order, can anything ever truly be lost? What if the ground beneath your feet, the very fabric of reality, wasn't as solid as it seems? Not in a metaphorical sense, but literally. The universe we know might be perched on a razor's edge, one quantum fluctuation away from total annihilation. This is the spine-chilling premise of the false vacuum catastrophe, a theory suggesting our cosmos could be living on borrowed time. Picture the universe like a ball resting in a valley, stable for now, but with a far deeper valley lurking just beyond the ridge. A nudge in the right direction, and the ball could tumble into that lower state, rewriting the laws of physics in an instant. The danger lies in the Higgs field, an invisible energy field that permeates all of space and gives particles their mass. Right now, it's in what physicists call a false vacuum, a seemingly stable state that isn't truly the lowest energy configuration. Think of it like a frozen lake in winter. The ice appears solid, but beneath the surface there's liquid water at a lower energy state. If the ice cracks, the system collapses into that more stable form. Similarly, if the Higgs field were to quantum tunnel into its true vacuum state, it would unleash a bubble of destruction expanding at the speed of light, erasing everything in its path. The trigger could be anything or nothing at all. A random quantum fluctuation in deep space, a high-energy particle collision, even the accumulated probability over billions of years. Once initiated, the new vacuum state would propagate outward like a shock wave, altering fundamental constants as it goes. The speed of light, the strength of gravity, the very charges of electrons, all could change instantly. Chemistry as we know it would cease to exist, stars would wink out, life in any recognizable form would be impossible. The scariest part, you wouldn't see it coming. The wave would move too fast for any warning, rewriting reality before your neurons could even process the disaster. This isn't just speculation, the math checks out. The standard model of particle physics suggests our vacuum is metastable, balanced precariously between stability and collapse. Experiments at the Large Hadron Collider have narrowed down the Higgs boson's mass, and the numbers hint we might indeed be in that fragile false state. Some theorists argue that cosmic inflation's end could have been a similar phase transition, meaning it's happened before. Others point to the unnerving fact that the universe's dark energy density, the force accelerating its expansion, matches predictions for a vacuum on the brink of decay. Yet there's a bizarre silver lining. If a false vacuum collapse began, it would create a new universe with entirely different physics, one that might be far more hospitable to life than our own. In this scenario, our cosmic demise could be the birth of another reality, like a phoenix rising from the ashes. Still, for those of us fond of existence as we know it, the false vacuum hypothesis serves as a humbling reminder. The universe isn't just vast and mysterious, it might also be far more fragile than we ever dared to imagine. In 1972 and 73, NASA launched the Pioneer 10 and 11 probes, twin spacecraft destined to become the first human-made objects to journey beyond the solar system. But as they raced toward the stars, scientists noticed something bizarre. Their speed didn't match predictions. Anomalies happened, but this was different. The Pioneers were slowing down more than Newton's laws could explain, as if some unseen hand was gently tugging them backward. This tiny discrepancy, just a fraction of a nanometer per second squared, became one of the most stubborn mysteries in space exploration, the Pioneer anomaly. At first, engineers suspected mundane causes. Maybe it was heat radiating unevenly from the probe's power systems, giving them an imperceptible push. Or perhaps fuel leaks were altering their trajectories, but after years of analysis, the numbers refused to cooperate. The deceleration was too consistent, too uniform across both spacecraft. Something deeper was at play, something that challenged our understanding of gravity itself. Could this be a crack in Newton's edifice, a hint that Einstein's relativity wasn't the final word? Enter dark matter, the universe's most elusive architect. If a diffuse halo of invisible particles enveloped our solar system, its gravitational pull might explain the Pioneer's slowdown. But there's a problem. Dark matter's effect should influence planets too, and no such anomalies appear in the orbits of Neptune or Pluto. Unless dark matter clumps in ways we've never seen, this explanation feels like fitting a square peg into a cosmic round hole. Then there's modified gravity, the idea that our formulas break down at certain scales. Theories like modified Newtonian dynamics propose that gravity behaves differently under extremely weak accelerations, like those experienced by the pioneers in the solar system's far reaches. It's a radical notion, but one that elegantly sidesteps the need for dark matter. Yet struggles to explain other astrophysical observations, leaving many physicists unconvinced. The plot thickened when New Horizons, the Pluto-bound probe launched in 2006, didn't experience the same anomaly. Was the effect unique to the Pioneer's design? Or had the universe's rules subtly shifted in the decades between missions? The answer came in 2012 when a team meticulously reconstructed the Pioneer's thermal emissions. Turns out heat was the culprit after all, not from leaks, but from the spacecraft's radioisotope power sources radiating warmth unevenly, creating a tiny but measurable recoil. Case closed, not quite. While most scientists accepted this explanation, a few holdouts argue the math doesn't fully account for the observed deceleration. The Pioneer anomaly's legacy endures not as proof of new physics, but as a testament to science's self-correcting nature. It reminds us that even the smallest deviation can spark profound questions, and that the universe's greatest puzzles often hide in the details we overlook. Whether future missions uncover deeper mysteries or confirm the thermal hypothesis, one thing's certain: the Pioneer's journey taught us humility. After all, if a speck of heat can upend decades of speculation, what other secrets might the void be keeping? Deep in the cosmic void, hidden behind the dense stars of our own Milky Way, lurks something enormous, something pulling thousands of galaxies, including ours, toward it with irresistible force. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it warps the motion of entire galaxy clusters across hundreds of millions of light-years. Yet despite decades of study, its true nature remains one of the universe's most tantalizing enigmas. Is it a colossal supercluster, a gap in our understanding of gravity, or evidence of something far more extraordinary? The story begins in the 1970s when astronomers first noticed something odd about the local universe's motion. Even after accounting for the expansion of space, galaxies in our galactic neighborhood, including the Milky Way, were drifting toward a single point in the constellation Centaurus at nearly 1,000 miles per second. This wasn't just random drift. Something massive, something unseen, was tugging on the cosmic fabric. Early calculations suggested an object with the mass of tens of thousands of Milky Ways, concentrated in a region roughly 400 million light-years away. But when scientists pointed their telescopes in that direction, they found nothing, or at least nothing matching the expected scale. The problem: our view was blocked. The Great Attractor lies in what astronomers call the zone of avoidance, an area obscured by the dust, gas, and blinding starlight of the Milky Way's disk. It's like trying to spot a distant mountain through a blizzard. Only with the advent of X-ray and infrared telescopes could we peer through the cosmic fog, and what we found only deepened the mystery. There was a massive concentration of galaxies there, the Laniakea supercluster, a web of hundreds of thousands of galaxies spanning 500 million light-years. But here's the catch: Laniakea's gravity alone couldn't account for the observed pull. The great attractor seemed to be something within or beyond it, a hidden driver behind the motion. One theory points to dark flow, an even larger and more perplexing phenomenon. Observations of distant galaxy clusters suggest they, too, are moving toward something beyond the observable universe, as if our entire cosmic neighborhood is caught in a current flowing toward an unfathomably massive structure. Could the Great Attractor be just a local manifestation of this grander motion? Some models propose superclusters, agglomerations of matter so vast they defy conventional cosmology. Others wonder if we're seeing the fingerprints of a primordial flaw in the fabric of spacetime itself, a relic from the universe's birth that warps gravity on epic scales. Then there's the radical possibility: our models of gravity are incomplete. Modified Newtonian dynamics suggests that gravity behaves differently at galactic scales, potentially explaining anomalous motions without invoking unseen mass. Yet most astronomers remain skeptical, citing the overwhelming evidence for dark matter. Still, the Great Attractor's grip on our curiosity is undeniable. Every new observation, like the discovery of the Vela supercluster, a previously hidden neighbor adding to the gravitational puzzle, brings us closer to an answer, or perhaps to a deeper question. What makes this enigma so compelling isn't just the unknown mass. It's the reminder that the universe operates on scales we're still struggling to grasp. The Great Attractor could be a signpost pointing to deeper layers of cosmic structure, or a clue that our corner of reality is caught in a flow older than time itself. Until we develop telescopes capable of seeing through galactic interference or unlock new physics to explain its pull, this mysterious force will remain a gravitational siren, luring us toward revelations just beyond our reach. The cosmic microwave background, the afterglow of the Big Bang, should be the universe's most democratic feature, a near-perfectly uniform canvas of ancient light. Yet hidden within its subtle temperature fluctuations lies something that shouldn't be there, a strange, unexplained alignment cosmologists half-jokingly dubbed the axis of evil. This eerie pattern, a preferential direction in the CMB's fluctuations, defies the core principle of isotropy, the idea that the universe looks the same in all directions. Instead, it hints at a cosmic architecture older than time itself, a fingerprint from before the dawn of our reality. First detected in 2005 by NASA's WMAP satellite and later confirmed by Planck, the axis of evil isn't some malevolent force. The name plays on its defiance of cosmological expectations. Imagine tossing confetti in the air. You'd expect it to scatter randomly. But if the pieces landed in a clear line pointing toward, say, the constellation Virgo, you'd suspect someone rigged the toss. That's essentially what we're seeing. The hot and cold spots of the CMB, which should be randomly distributed, instead show a peculiar alignment along a specific axis. The odds of this happening by chance, less than 1 in 100. Skeptics argue it's just a fluke, a statistical anomaly amplified by our human tendency to find patterns in noise. After all, the CMB is incredibly subtle, with temperature variations measured in millionths of a degree. Maybe we're seeing cosmic pareidolia, like finding faces in clouds. But the persistence of the signal across multiple missions has forced even the most cautious scientists to consider alternatives. Could it be contamination from our own galaxy's dust? Unlikely. The alignment persists even after meticulous filtering of local interference. Then there's the radical possibility. The axis of evil is a relic of a pre-Big Bang structure. Some theories, like conformal cyclic cosmology, propose that our universe is one in an endless chain, with each cycle's end seeding the next Big Bang. If true, the axis could be a scar, a gravitational imprint from a previous cosmic era, like a bruise that never fully faded. Other models suggest it's evidence of a multiverse, where neighboring universes exert tidal forces on ours, tugging space-time into an asymmetrical shape. Picture bubbles in a foam pressing against each other and leaving subtle deformations at their borders. Wilder still is the quantum entanglement explanation. If particles in the early universe were entangled across vast distances, a phenomenon allowed by quantum mechanics, their correlations might have etched directional preferences into the CMB. It's as if the universe's quantum skeleton is poking through the flesh of classical physics, revealing a hidden scaffolding beneath. The stakes are high. If the axis of evil is real, it could upend cosmology's holy grail, the cosmological principle which assumes the universe is homogeneous and isotropic on large scales. Toss that out and suddenly our maps of dark matter, our understanding of cosmic inflation, even our estimates of the universe's age might need recalibration. Future telescopes, like the proposed CMB S4 project, could settle the debate by mapping the CMB with unprecedented precision. Until then, the axis of evil remains either cosmology's most tantalizing clue or its most stubborn illusion. Either way, it forces us to confront an unsettling truth. The universe might not be as random or as alone as we once believed. What if the universe has a beating heart, a supermassive black hole so colossal it shapes the fate of everything around it? Not the familiar black holes lurking in galactic centers, but something far grander, a primeval singularity anchoring the entire cosmos, its gravitational influence stretching across billions of light years. This isn't just fantasy. Some theories suggest such a monster could exist, hidden in the void, its pull so vast it might even be driving the universe's accelerating expansion. Imagine a spider at the center of a web, each thread a filament of galaxies tensing under its invisible force. The idea emerges from a simple but haunting question: why is the universe expanding faster than our models predict? Dark energy is the usual suspect, but its nature remains a mystery. Could a central black hole, or something like it, offer an alternative? Einstein's equations allow for solutions where a sufficiently massive singularity could warp space-time on cosmological scales, creating effects indistinguishable from dark energy's repulsive push. Picture a rubber sheet stretched taut with a bowling ball at its center. Now imagine that ball warping the sheet so profoundly that distant points begin sliding away from each other, not because they're being pushed, but because the fabric between them is fundamentally altered. There's precedent for this kind of influence. We already know supermassive black holes govern their galaxies, with masses tightly correlated to the host galaxy size. Their gravity shapes star orbits, fuels quasars, and even regulates star formation. Scale this up to cosmic proportions, and a universe-anchoring black hole could be the ultimate puppet master. Some models propose it formed in the instant after the Big Bang, a primordial singularity that avoided evaporating by feeding on the dense energy of the infant cosmos. Others suggest it's the remnant of a previous universe, a relic from a cycle of cosmic rebirth. But how would it work? Unlike dark energy, which is imagined as uniformly permeating space, a central black hole's influence would diminish with distance. Yet if the universe's expansion is accelerating uniformly everywhere, how could a single point explain it? Here's where things twist. The black hole wouldn't need to pull galaxies directly. Instead, its gravity might alter the vacuum of space around it, creating a kind of pressure gradient that drives expansion. Think of blowing up a balloon with a weight taped inside the rubber stretches unevenly, with regions farther from the weight expanding faster. If our universe has a similar asymmetric anchor, it could mimic dark energy's effects while offering a concrete mechanism. The challenges are obvious. For one, we've never detected such an object, and the cosmic microwave background shows no obvious signature of a preferred central direction. Then there's the scale problem. To influence the entire universe, this black hole would need mass exceeding trillions of suns, bending the limits of what we think singularities can achieve. Yet black hole cosmology isn't entirely fringe. Renowned physicist Nikodem Poplawski has proposed that our universe might exist inside a black hole in a parent universe, with the Big Bang as the singularities rebound. If true, the center of our cosmos might not be a point in space, but a condition inherited from higher dimensional physics. Whether this theory holds or not, it forces us to confront the limits of our cosmic maps. We're like ants on a Mobius strip, tracing paths that seem straight but might curve in ways we can't perceive. If the universe has a hidden heart, its rhythm could be written in the redshift of galaxies, the clustering of dark matter, or even the faint whispers of gravitational waves. Until we find it or rule it out, the possibility remains that the greatest structure in existence isn't a web or a field, but a darkness so vast it shapes the light. Picture the universe as a vast, shimmering web, not one woven from strands of silk, but from threads of quantum entanglement, the mysterious link that binds particles across cosmic distances. What if this intricate network isn't just a feature of reality, but the very fabric from which spacetime itself emerges? This is the radical promise of the E=EPA conjecture, a theory so elegant it ties together two of physics' most mind-bending concepts, wormholes and quantum entanglement. Start with entanglement, that eerie phenomenon where particles become inextricably linked, sharing states instantaneously no matter how far apart they drift. Measure one electron's spin as up, and its entangled partner will always be down, even if they're on opposite sides of the galaxy. Einstein famously dismissed this as spooky action at a distance, but experiments have proven it's real. Now imagine those entangled pairs aren't just connected abstractly, but physically, via microscopic wormholes, Einstein-Rosen bridges, threading through spacetime like stitches in cosmic cloth. That's the essence of ER=EPR, a proposal by physicists Leonard Susskind and Juan Maldacena suggesting that entanglement EPA, named after Einstein, Podolsky, Rosen, and wormholes are two faces of the same coin. Here's where it gets fascinating. In quantum mechanics, entangled particles share information without any direct signal passing between them, defying classical notions of locality. Meanwhile, general relativity describes wormholes as shortcuts through spacetime, where distant regions are connected by warped geometry. ER=EPR posits that these aren't separate phenomena, they're the same thing described in different languages. An entangled pair of black holes, for instance, might be joined by a wormhole too tiny to traverse, a hidden tunnel encoding their correlation. On the quantum scale, this could mean every entangled particle in the universe is invisibly stitched together by spacetime threads too minute to detect. The implications ripple outward. If spacetime emerges from entanglement, then the smooth, continuous universe we perceive might be an illusion, a hologram projected from a deeper, more fundamental network of quantum links. Think of it like a pixelated image. Zoom in close enough and you'll see the individual dots, but step back and they blend into a seamless picture. This could explain why black holes preserve information rather than destroying it. The data isn't lost inside the singularity, but preserved in the entangled web connecting the whole to its surroundings. Even the Big Bang might find a new interpretation, a cosmic, untangling event where the primordial universe's quantum connections froze into the spacetime structure we know today. Critics argue the math remains speculative, and bridging quantum mechanics with gravity is notoriously thorny. Yet experiments are already probing the idea. Researchers have simulated entangled wormholes in quantum computers, observing behavior that mirrors theoretical predictions. Others study the entanglement entropy of spacetime itself, hunting for signatures of this hidden architecture. If validated, AR equals EPR could revolutionize our understanding of reality, revealing a universe where distance and separation are illusions, and where the deepest layers of existence are woven from quantum threads we've only begun to trace. So the next time you hear about entangled particles or wormholes, remember, they might not be separate mysteries, but different glimpses of a single, breathtaking truth that the universe is quite literally held together by invisible knots of quantum connection, tying everything from atoms to galaxies into one inseparable whole. The universe unfolds in patterns so vast and intricate, they seem almost artistic galaxies clustered into filaments, swirling like brushstrokes across the void. Now imagine zooming in or out and finding those same patterns repeating endlessly, from the tiniest quantum fluctuations to the grandest superclusters. This is the heart of fractal cosmology, a theory suggesting the cosmos isn't just structured, but self-similar at every scale, like a cosmic Russian nesting doll where each layer mirrors the whole. The idea builds on fractals' mathematical shapes where tiny sections resemble the entire form, whether in a snowflake's branching arms or a coastline's jagged edges. Apply this to the universe and you get a model where galaxies cluster into groups. Those groups form larger clusters and so on with no clear endpoint. Astronomers have long noticed this hierarchy. Peering through telescopes, they see galaxies grouped into filaments and walls, separated by vast bubbles of emptiness, a cosmic web uncannily similar to neural networks or the branching veins of a leaf. But here's the twist: if this pattern holds infinitely, it could overturn foundational assumptions about the Big Bang and the universe's very origin. Proponents argue fractal cosmology explains anomalies in cosmic surveys. For decades, astronomers assumed matter would distribute evenly at the largest scales, a principle called homogeneity. Yet maps of galaxy distributions keep revealing clumping at ever grander magnitudes, with some structures spanning billions of light years. Like the Hercules Corona Borealis Great Wall, a galactic filament so colossal it challenges the notion of a smooth universe. If the fractal pattern persists, it might mean there's no true, average density of matter, just an endless recursion of clusters within clusters. This wouldn't just tweak our cosmic maps, it could force a rethink of dark matter's role, or even suggest gravity behaves differently at vast scales. Critics, however, point to the cosmic microwave background. The Big Bang's afterglow shows near uniformity, with temperature variations so slight they imply a fundamentally smooth early universe. How could a fractal structure emerge from such homogeneity? Some theorists propose an exotic solution. Inflationary physics might have imprinted fractal patterns as space-time expanded, like stretching a crumpled sheet until its wrinkles appear at all scales. Others speculate the universe's fractal nature hints at something deeper, a cyclic cosmology where each layer represents a phase transition, like bubbles in a multiversal foam. The most radical implications concern the Big Bang itself. If the universe is truly fractal without a largest or smallest scale, then the idea of a singular beginning starts to fray. Instead, we might live in a fractal flake within an eternal, uncontained cosmos, where beginnings and ends are local events in an infinite cascade. Picture a tree growing in a forest. Each branch splits into smaller twigs, but the tree itself is just part of a larger ecosystem. Similarly, our observable universe could be one branch of an unending fractal with no definitive root. Fractal cosmology remains controversial, but its allure is undeniable. It merges mathematics with mythology, echoing ancient ideas of as above, so below. Whether it ultimately reshapes astrophysics or remains a beautiful metaphor, the theory invites us to see the universe not as a void dotted with objects, but as a living pattern, an infinite tapestry whose threads weave the same story at every scale. The next time you gaze at a spiral galaxy, consider its swirling arms might not just resemble a hurricane or a seashell. They could be a whisper of the cosmos' deepest secret, that the universe is less a place than a pattern repeating itself into eternity. What if every electron in the universe, every particle powering the glow of stars, the circuits in your phone, even the neurons firing in your brain wasn't a separate entity at all, but the exact same object dancing through time like a cosmic echo? This is the breathtaking premise of the one-electron universe, a theory proposed by physicist John Wheeler in a casual conversation with his student Richard Feynman in the 1940s. Picture a single electron zigzagging through time like a thread stitching reality together, moving forward to become the particles we see, then looping backward as their antimatter counterparts. It's a concept so audacious it blurs the line between physics and philosophy, suggesting that the staggering complexity of the cosmos might stem from something deceptively simple. Start with antimatter, the mysterious twin of ordinary matter. For every electron, there's a positron, identical in mass but with opposite charge. When they meet, they annihilate in a flash of energy. Standard physics treats them as distinct particles, but Wheeler's idea flips this on its head. Imagine that positrons aren't separate entities at all, but electrons traveling backward in time. It's like watching a movie reel in reverse. The electron's path forward appears as matter, while its rewind appears as antimatter. Feynman later formalized this in his diagrams, where antiparticles are represented as particles moving backward along the time axis. The math works flawlessly, a tantalizing hint that Wheeler's intuition might have tapped into something profound. But how could one electron account for the countless particles we observe? Here's where the theory gets truly wild. If time is infinite, that single electron could weave back and forth endlessly, appearing at every point in spacetime where an electron or positron exists. Think of it like a single actor playing every role in a cosmic play, darting on and off stage so quickly the audience sees an entire ensemble. The universe's vastness wouldn't require countless particles, just one, endlessly reused. This isn't just poetic, it solves a deep mystery about symmetry. Why do electrons all have identical mass and charge? Because in this view, they're literally the same thing. The implications ripple through quantum theory. If particles are threads in time rather than distinct objects, it could explain entanglement, the eerie link between particles that defies classical physics. Two separate electrons might actually be the same particle touching multiple points in spacetime, their correlation baked into the fabric of existence. Even the arrow of time becomes fluid. In Wheeler's universe, the distinction between past and future might be a side effect of perspective, like calling a mountain's ascent and descent different journeys when they're just two phases of one hike. Critics, of course, raise objections. The theory struggles to account for particle interactions that don't involve electrons, like quarks inside atomic nuclei. And if positrons are electrons moving backward, why doesn't the universe have equal amounts of matter and antimatter? Yet even as a thought experiment, the one-electron universe reshapes how we see reality. It suggests that the building blocks of existence might not be scattered like Lego bricks, but woven together in a tapestry where time is just another dimension to traverse. So the next time you charge your phone or watch a lightning bolt split the sky, consider this. The electrons dancing through those moments might not be tiny strangers but familiar faces, the same traveler greeting you again and again from different points on its endless journey through time. Whether the theory holds or not, it reminds us that the universe's deepest truths often lie not in complexity, but in simplicity so radical it takes our breath away. The universe thrums with whispers from its birth, not just in the light we see, but in ghostly particles streaming through your body right now, unnoticed. Among these cosmic specters, neutrinos reign supreme, nearly massless, chargeless particles so elusive they pass through entire planets like they're barely there. Yet within their subtle dance lies a relic more ancient than starlight, the cosmic neutrino background, a fossilized echo of the universe's first second. Imagine capturing whispers from the dawn of time itself, not etched in light like the cosmic microwave background, but in particles that barely interact with reality at all. This neutrino sea was born just 1 second after the Big Bang, when the fiery plasma of the infant universe cooled enough to let these phantoms decouple and stream freely across the cosmos. While photons, the particles of light, were still crashing into matter, trapped in the primordial soup for another 380,000 years, neutrinos were already racing outward, carrying snapshots of a universe we've never seen. Today, they permeate every cubic inch of space, a cosmic undercurrent flowing at nearly the speed of light. But here's the catch: their very elusiveness makes them maddeningly hard to detect. Unlike the cosmic microwave background, which we've mapped in exquisite detail, the neutrino background remains a shadowy enigma, its secrets locked behind interactions so rare, even mountains of sensitive equipment struggle to spot them. Why endure the hunt? Because neutrinos could be the ultimate cosmic historians. Their properties, especially their tiny, puzzling masses, might hold clues to physics beyond the standard model. Some theories suggest neutrinos could bridge the gap to dark matter, interacting with the universe's invisible scaffolding in ways we've yet to imagine. Others propose that slight asymmetries in their behavior might explain why matter triumphed over antimatter in the early universe, allowing galaxies, planets, and us to exist at all. Even their sheer numbers are staggering. For every proton in the cosmos, there are roughly 1 billion neutrinos. If we could decode their faint signals, we'd gain a lens into epochs before atoms formed, when the universe was a seething, quark-gluon plasma too hot for even nuclei to survive. Detecting this background isn't just a technical challenge, it's a feat of cosmic eavesdropping. Modern experiments like IceCube, buried deep in Antarctic ice, or Super Kamiok, and a tank of ultra-pure water beneath a Japanese mountain wait patiently for the rare neutrino collision. But the cosmic background neutrinos are so low energy that they slip through these detectors like mist through a sieve. Future proposals aim to catch them by watching for minuscule energy transfers in ultra-cold solids or quantum sensors so precise they can sense a neutrino's feather-light touch. Success would open a window into the universe's first moments with a clarity no telescope can match. The stakes couldn't be higher. If dark matter interacts with neutrinos, their background could map its distribution like sonar pinging through an abyss. Variations in their density might reveal primordial black holes or hidden dimensions crumpled at microscopic scales. And if neutrinos oscillate differently in the gravitational wells of ancient galaxy clusters, they could expose the fingerprints of cosmic inflation, the universe's explosive growth spurt. Every undetected neutrino is a messenger from a time before time, carrying stories we've only begun to imagine. So next time you feel nothing, remember, you're bathed in a sea of ghosts, each one a silent witness to the birth of everything. Time, the invisible river carrying all existence from past to future, feels as permanent as the stars. But what if one day that river simply dries up? Imagine a universe where clocks stop not because they break, but because time itself ceases to have meaning. This isn't science fiction, it's a genuine possibility lurking in the far future, where the very fabric of reality unravels into stillness. Start with heat death, the most haunting forecast for the cosmos. Picture a universe expanding forever, galaxies drifting so far apart that their light can never bridge the gaps. Stars burn out, black holes evaporate, and matter itself decays into faint whispers of radiation. In this frozen era, entropy, the measure of disorder, reaches its maximum. Everything settles into perfect equilibrium, like a cup of coffee cooling to room temperature, never warming up again. But here's the twist: without temperature differences or energy gradients, no processes can occur. No chemical reactions, no motion, no change of any kind. Time becomes obsolete, a concept with no events to mark its passage. It's not that time stops, it's that the idea of before and after loses all relevance. The universe doesn't end with a bang or a whimper, but with a silent, eternal sigh. Yet there's another, more violent possibility: quantum vacuum decay. Our universe might be perched in a false vacuum, a metastable state like a ball balanced on a hill. A random quantum fluctuation could tip the system into a true vacuum, unleashing a bubble of destruction. This bubble would expand at light speed, rewriting the laws of physics as it goes. Inside it, time could behave in ways we can't fathom, flowing backward, fracturing into loops, or ceasing altogether. Some models suggest the new vacuum might lack the dimensions needed for time as we know it, leaving a reality where cause and effect no longer apply. The chilling part: this could happen at any moment with no warning. How would physics adapt to timelessness? Without time, equations describing motion or change become meaningless. Thermodynamics, the study of energy flow, would collapse since heat can't disperse in a static universe. Even quantum mechanics, with its probabilistic nature, relies on time to define states. Some theories propose that in a frozen cosmos, information might still exist, frozen in an eternal snapshot. Others speculate about static universes where all possible states coexist simultaneously, like frames of a movie stacked atop one another. Philosophers have long debated whether time is fundamental or emergent. Its disappearance could reveal it was never more than a useful illusion, a side effect of entropy's march. The most profound question isn't how time ends, but what remains when it does. Could consciousness, in some form, persist in a changeless void? If time is just a human construct, does its end even matter? These aren't just thought experiments, they're windows into the universe's deepest nature. Whether time vanishes in ice or fire, its end would rewrite existence itself, leaving a reality stranger than we dare imagine. From the holographic universe whispering its secrets in 2 dimensions to the eerie possibility that we're living in a simulation, every theory we've explored today shatters our assumptions about reality. Each one isn't just a wild guess, but a rigorous challenge to the limits of human understanding, proving the cosmos is far stranger than we ever imagined. Whether it's dark matter's invisible grip sculpting galaxies or the Boltzmann brain paradox suggesting you might be a fleeting illusion, these ideas don't just bend minds, they snap the very framework of what we think we know. Consider the implications. If the universe cycles eternally through big bangs and big crunches, then every star, every planet, every moment of consciousness is destined to repeat infinitely. If quantum entanglement stitches space-time together with invisible threads, then every choice you make might ripple across dimensions. And if time itself is an emergent illusion, then the past and future could be as fluid as dreams. These aren't abstract thought experiments, they're invitations to see existence through a radically different lens. So what's next? The greatest discoveries lie at the edge of our curiosity. Maybe you're convinced by the fractal cosmos, where patterns repeat from atoms to superclusters, or perhaps the Mandela effect's glitches hint at parallel realities bleeding into ours. Whatever resonates, remember, science thrives on questions, not just answers. The universe's deepest truths often start as heresies before becoming textbooks. Now it's your turn. Drop your favorite theory in the comments. Was it the black hole universe, the haunting Fermi Paradox, or something else that rewired your brain? Let's keep the conversation cosmic, and if you're hungry for more mysteries, hit subscribe. From phantom energy's apocalyptic rip to the quantum code that might underpin reality, we've only scratched the surface. The universe is waiting to unsettle us again, and you won't want to miss what comes next. Until then, keep looking up and questioning everything.